Stone groins such as these are spread all over Denmark. They are built to protect the coastline from erosion. It has however taken materials from the ocean to build them. In Denmark, it is estimated that stone fishing has relocated more than 8 million cubic meters of hard bottom substrate from Danish shallow waters. Most of our shallow waters are sandy. Many species require hard bottom substrate, such as this granite, to latch onto. This master thesis aims to give back habitat for both plants and animals by testing new materials suitable for artificial reef construction. Two porous concretes are tested against two controls. The first porous variant, aerated autoclaved concrete with closed pores, this white one. The second porous variant is an open pore, pervious concrete, with lightweight expanded clay aggregate known as leca. The first control is a natural granite, often used for reef construction. Due to the hardiness of granite, we were not able to manipulate the material into the cylindrical shapes of the other specimen. The second control is a more typical construction concrete with medium to high strength, similar to what would be found on a typical harbor wall. But let's first go back in time to explore the origins and reasons for choosing these concretes for testing. In a process known as biogenic precipitation, small marine organisms contributed to forming the limestone deposits we see here in Denmark today. To create Portland cement, limestone is heated in a process known as calcination that chemically releases bound CO2. Mixing this cement with water starts the hydration process where concrete as we know it is formed. But there is one third and final stage to this, where concrete begins to recarbonize from CO2 available either from the air or from the water. A fully recarbonized concrete could potentially halve the emissions footprint. Maximizing carbonization should require more surface area. So let's get on to testing if porous concretes also holds any ecological value. A holding structure, in this case a steel rack, was constructed to hold the cylindrical specimens. They hold 16 specimens each, so for the 64 total specimens, 4 racks were needed. Now for gathering the specimens themselves. The inexpensive test variants were acquired as blocks, then core samples were drilled from them. This revealed the complex inner microstructure of the materials, seen here under the microscope.
Alle liggeprøverne og alle gasbetonprøver og
This is me. Hi there. In demolding the construction concretes, it was seen how one surface was very smooth and one had some exposed aggregates, providing more complexity. Artificially exposing aggregate like this was one of the early suggestions to have a higher surface complexity for more settlement. The construction concretes were cured in hot water bath to accelerate their hardening, but was left for a little too long, as the maturation stage would be equivalent to the 34th day strength. These cobblestones are officially not a part of this project, but were included as a parallel project very similar to this, co-led by supervisor to the project, Susanne. Here's Claus Falconi, CEO of Falconi Mara,
jeg er her sammen med
and our contact at Dansk Tang. Dansk Tang agreed to lending us space in their ocean farm, very close to where they grow seaweed commercially for human consumption. At the placement of the specimen, it is very much noted how the two porous concretes actually floats toward the top of the rack, while the heavier granite and construction concrete sinks towards the bottom. It was not fitted in this shot, but a camera was later mounted to Unit 2 to document the growth developing on the specimen. The camera was fitted with software to take shots during the day and turn off by night to conserve battery. Unfortunately, this software proved faulty. Instead, the units had to be inspected manually, sometimes on land due to poor visibility. One of the test materials, the AAC, actually did seem to outperform the others in ecological value, as it had more discoloration and algal growth on the surface area. However, the AAC was also the sample most affected by the wave action, moving the specimen and grinding them away from the inside. These durability issues were of course worrisome, but were concluded to be caused by the rack that wouldn't exist in an actual reef. It was noted that all specimens suffered a decline in algal growth, possibly due to the seasonal changes or to severe winter storms. Granite samples were seemingly bare of all algal growth, but had the most abundance of snails. This preference could stem from a chemical composition of the natural granite. The construction concrete fared the second best, with some algal growth left, but its smooth surfaces proved too slippery for the algae to hold on to. The Liga concrete arguably fared the worst. It had little to no algal growth. This partly disproved porosity as the most important ecological trait for concretes. The AAC seemed to perform the best out of all the materials. The complexity at the surface seemed to retain algae growth better. These results were very much mirrored in another project which was terminated during this thesis. Here, different concrete tiles were examined for their ecological value using different textured surfaces. These tiles were exposed for much longer than the concretes we just saw, but has also experienced many different types of seaweed during the season. Here they are examined for the final time.
De plasker de her ind fra hende, og den midterste sten, den var jo stort set meget mindre. Det hører til herovre. Den har helt generelt været meget mindre på.
It was concluded that due to the runoff when a wave hit the top of the rack, the increased velocity would wash off small seedlings. Hydrodynamics aside, both tests show how seasonal changes affect new reefs in particular. Acquiring more stable ecosystems requires more perennial plants, like this one, Saccharina latissima, which is the subject of analysis in the lab test. This test was done alongside in a similar way to the test you saw in the oceans. It was done to determine the effectiveness of preceding elements before putting them into the ocean, to see whether a more stable ecosystem would develop more rapidly. Preceding is already done in the industry, but it's not done directly on concrete, but instead indirectly on spore lines such as these. Spore lines are then later attached to buoys with ropes. The spatial effectiveness of indirectly seeding is here clearly visible, as many meters of spore line can be germinated in a much smaller footprint that are also much easier to manage than large heavy concrete blocks.
Vi fik i sidste øjeblik rekvireret de her plastikhætter her, som faktisk fungerer som vride til en gulvflud.
Det var det.
Ja, det var det var. Så normalt så vender den sådan her i en spand.
Acquiring mature source tissue, which is the fertile part of the plant, proved very difficult. Fortunately, a contact at Dansk Skaldyrscenter came through and gave us this lab-grown seaweed. This seaweed was then cleaned and plucked off any epiphytes. At this stage would normally be created what is known as a breaker or spore soup, but due to the large quantities of water in the tank, another approach was taken, recommended to us by Dansk Skaldyrscenter. This method would simply have the seaweed sit in the tank to release as many seedlings as possible. The method would later be altered due to the seaweed sitting too still in the tank possibly favoring some of the specimen. And when Saccharina latissima began maturing in the wilds, a more traditional approach to seeding was also done in the form of known quantity breakers. While the spore soup developed here was of a fair concentration, due to the quantity of water used, it came down to approximately 1/10 of the recommended concentration. Similar to in the field test, the AAC proved to develop more rapidly than the other concretes and retain the growth it acquired better than the other samples. The performance ranking of the rest of the samples was also similar to in the ocean, where the second would be the construction concrete, third the granite, and then last the lacquer. At this stage, it was determined that settling was over, and the diffusal layers holding back the light intensity were removed. Increasing the light intensity clearly increased the growth of the samples, but also had some unintended effects. As the light came from directly above, the samples more in the center would experience more growth than samples at the edge of the tank. As the materials themselves could not go under the microscope, proxies had to be used in order to gauge the species in the tank. To further dissuade diatoms from overtaking the entire tank, germanium oxide was added. Approximately 2 months after the first seaweeds were added to the tank, and 1 month after the second release. This is the state of the tank. Many of the samples are affected by the addition of germanium oxide, as seen by the clear decrease in algal growth on all samples. The rank ordering of what was left was still the same, with the AAC still retaining the most algal growth. Some of the growth was green, remembering that Saccharina latissima is a brown algae. This could not be the seaweed we were looking for. Some brown discoloring still remained on all samples. Hopefully, this is the model species we're looking for. Neither of the experiments you so far seen are terminated yet, but are to be combined in a third and final experiment, comparing the pre-seeded samples, possibly at a new location, and possibly with a reconfiguration of the rack that caused durability issues, placed in the wild in Rørvig. A lot has been learned from both these experiments, but now this thesis has come to an end. Thank you for watching. Have a nice day.